So today we're going to start talking about energy. And energy is absolutely important when we talk about chemistry because you can have energy that's either produced in a reaction or something that is required for a reaction. So energy is the ability to do work. So what does that mean for work? Well, technically work is what occurs when you move matter or an object against a force. In other words, you're actually pushing something. That's what that means, like pushing against a piston or whatever it may be. So there's two major kinds of energy. There's potential energy. So this is kind of like stored energy. And that could be by the placement of an item, like water at the top of a waterfall. Or it could be stored as a chemical bond. And then we have kinetic energy. And so this is the energy of motion. We just talked about that a little bit when we were talking about gases. Next, we have temperature. As we talked about with gases as well, temperature and thermal energy in general is related to kinetic energy. It relates to how much molecules are moving around. The more they move, and they can move in single lines, or they can vibrate or wiggle or waggle and do all kinds of little dancing things. All of that is kinetic energy. And the average of that energy is what we define as temperature. So, hot materials are in motion more than cold materials. This actually relates to what happens in the microwave. So say you put something into the microwave. What happens is you're exciting the water molecules. That's the wavelength the microwaves hit at. It excites the water molecules. It makes them wiggle and jiggle and start dancing. And that's the reason why your food warms up, is because on average, things are vibrating and moving more. It also is the reason why rice gets dried out in the microwave, because you have a lot of steam that develops. Most substances expand as their temperature increases. And so why does this make sense? Well, as molecules move around and wiggle and jiggle, they need more space to move. Now, water is an exception for other reasons, but we'll talk about that some other day. Okay, this is a very important set of diagrams. We have things that are exothermic reactions. In other words, they produce heat or release heat. And we have endothermic reactions. These reactions will absorb heat and they feel cold to the touch. So you all have held hand warmers. Those produce heat. You've probably also gotten some of those packs that you can like mix together and they get cold. That would be an endothermic reaction because it's literally taking the energy out of your hand or your knee or wherever it's sitting in order to do these things. And we typically show these as reaction diagrams or energy reaction diagrams. And so that's what these guys are here and here. We have energy on the y-axis. So energy is increasing as we go this direction. And we say that this is the reaction progress. So what that means is time. But there's no real unit here for the time. So just don't worry about that too much. And you can do that over here too. I'm just showing you this to show you the difference between an endothermic reaction and an exothermic reaction. So first, let's start with the exothermic reaction. We begin by seeing where on our energy scale the reactants are. After going through some type of process, the products have energy down here. So the difference between where we started and where we left is seen right there. The reactants have a higher energy than the products have. That means that this extra here was energy that was lost to the environment. And that's what we refer to as an exothermic reaction. Now, you may be wondering, what is that little hump thing all about? All this? Well, just like it might take motivation for you to get up in the morning and go to work or go to school, reactions need a little kick in the pants sometimes. And this is what we call the activation energy. But notice that this energy that goes up it comes back down to there too, right? So it kind of is like you put energy in, it comes back out. We don't consider that part of the gain or loss of energy of that particular reaction. Now, on the other hand, you could have different types of endothermic reactions. And here's the difference. The reactants start off at an energy level that's lower than what the products have. And that means that there is a net gain in energy of those materials. So in other words, they suck energy away from things around them. They require energy to make this reaction happen. And you still have this activation energy thing that goes up. And we don't worry about that too much for now, because that's sort of like coming up and going back down. But this guy, this net gain of energy, means that it's an endothermic reaction. So if your products have a higher energy than your reactants, that's endothermic. If your products have a lower energy than your reactants, then that's an exothermic reaction. The surrounding environment, by the way, is anything that's around. Okay? So we need to know some of the terms that we're going to use in energy calculations. Just the same way when we were dealing with gases, we needed to know what pressure was and that type of thing. Well, within energy, we're going to start by looking at the term of heat. And heat is the transfer of thermal energy, in other words, temperature, kinetic energy type of stuff, between objects. Here's something that I didn't realize when I was taking general chemistry or before I did, and that is that heat moves from high concentration to low. So that means that the hotter object is actually transferring energy to the colder object. So if you have ice cubes in your drink, it's actually the water that's in your drink that's giving the cold part its energy. That also means that that energy is gone, and so it still cools off your drink. That's going to continue, like it'll keep on transferring energy from the liquid to the ice until there's no more ice, and they're both the same temperature. And that's sort of what we call equilibrium, which we'll talk about later. Okay, next we have calories. Now notice that this calories here has a little c. The calories is the amount of energy required to heat 1 gram of water 1 degree Celsius. Well, you've talked about calories before on any package that you get. You can see how many calories most of your foods require. Well, guess what? That's a big C, cal. That's actually a kilocalorie. So it's the amount of energy it takes to make 1,000 grams of water go up 1 degree centigrade. But you're a lot of kilograms of water, and 1 degree centigrade is standard for you. So it does take certain amounts of kilocalories to survive. Another form of energy is that of a joule, Joule. We put that as capital J. And this is the amount of energy required to move one object 1 meter with 1 Newton of force. Okay, what does that really mean? 1 little calorie is 4.184 joules. In other words, joules are tiny. And that means that you're going to have a large number there. A lot of times we talk about kilojoules instead for that very reason. Next, we have something called heat capacity. Now, realize that this is C, and it's a big C. And calories is CAL with a little c. Or we have calories over here with a big C. I don't know why we put all the same things with different things, like with the same abbreviation, but it is what it is, okay? And this is going to define heat capacity. So heat capacity is the amount of heat an object absorbs or releases when its temperature changes 1 degree centigrade. Now, I'm doing this delta T down here. Delta T is the change in temperature, and how you calculate change in anything, really, any of these deltas, it's temperature of the final thing minus the initial thing. That's going to become very important as we move forward because you need to know which one goes first. Negative values in math are about to change things. More commonly, instead of talking about heat capacity, we talk about specific heat capacity. This is little c. Or specific heat. That's another way to look at it. And this takes the amount of substance into account. So in other words, we said before that it was the amount that it takes, like how much energy it takes for an object to heat up. This takes grams into account. And so it's defined as the energy required to raise 1 gram of substance 1 degree Celsius, and that is therefore more useful. So the specific heat capacity is a given for various materials, and it is typically in joules over grams times Celsius, or it could be joules over grams times Kelvin. Q, we just talked about, is energy. And we've got M is mass and delta T right there. So this is a very common type of equation that you use. Now, I do want to point out the fact that since you're doing a change in T, in other words, delta T, it doesn't matter if you're using Celsius or Kelvin in the terms of C, because it can be used interchangeably. So if you have 273 Kelvin and you subtract 10 degrees, that's a delta T of 10. If you had those same values in Celsius and you subtracted 10 degrees, it's still going to be 10. So don't worry so much on that particular value. A good, very common example of using specific heat capacity would be you've got a specific, if the specific heat capacity for copper wire is this amount, how much energy is needed to raise 250 grams of wire from this temperature, 394, to 414 Kelvin? Well, all you have to do is find what your delta T is here. So in other words, your final minus the initial. That's going to be 20 degrees Celsius or Kelvin. You can use either one. And then you just plug things into the equation from above. So 0.390 is equal to Q divided by 250 grams times 20 Celsius. And that's how you find that Q is 1950 joules or 1.950 kilojoules. Either one of those is fine. Actually, it'd be 1.95 because we only have 3 sig figs here. Okay, thank you, and I'll see you when we talk about calorimetry next.